Good morning, everyone. Thank you for joining us. There we go. There's Kevin Slattery. Welcome, and we're glad that you could join us this morning. I'm Cynthia Rogers. I'm the communication advisor with the Barnes Advisors. It's great for us to see you here. I have a do I? Someone just messaged. All right, so I'm going to shut my microphone off and hand it over to Kevin Slattery, who is our host for today.
Well, thanks everyone for your interest in this topic and for attending. As I was mentioning at my table, the genesis of this topic was I was interested in learning more about reinforced polymer AM, and I thought, what better way than to host one of these things and get people together. And I presume you all have the same level of interest. So, you know, it's sort of the abstract mentioned, right? I really see this as an area that's really going to grow a lot in the next decade in AM. You know, standard polymer AM is, for lots of industries and lots of applications, the first process of choice. Metal is moving into there. You know, it's really moving into the industrialization stage. So in terms of developing the capability, reinforced polymers, I think is going to be a very exciting topic over the next decade. And today is right, you know, what is the difference between those and how are people addressing things we're going to talk about. So, so we have 5 panelists today, and I'll introduce them one at a time as they come on, but just sort of, so we have Mick Mayer from Mayer and Associates. Prior to that, he was with DARPA and with the US Army. Craig Neslin from AFRL, he's really going to focus on, you know, what are people wanting to see in these, really a requirement standpoint. What can they meet? And then we're going to have 3 people really talking about some emerging processes or current processes that are out there. Jeff DeGrange from Impossible Objects, Scott Turner from 3D Systems, and Nathan Strandberg from Continuous Composites. We're going to spend about 5 or so minutes each of them sort of talking about their topic and whetting our appetite. I'll then have about 15 minutes of questions. And so some open discussion, and then we'll have 15 minutes of questions, and then we'll break into our tables for half an hour for further discussions. So without further ado, I will pass the mic over to Mick and the video over to Cynthia, and we'll hear what Mick has to say about the topic.
Hey,
also,
thanks,
everyone,
Kevin.
I'm keeping the 5 panelists, I'm keeping check on the 6 questions and how you're addressing them, and they'll come back if you don't address them. Thanks.
We'll wait for them to come back because we'll just talk about what we want.
Yes, yes.
Hey, Kevin, so thank you, and thank you to the Barnes Group for kind of setting this up. You know, AM with reinforced polymers has been around a while. You know, I think as people, what's really firing up the new interest is that it's not just reinforced polymer now, but people are beginning to talk about providing properties that are consistent with like advanced composites. So for me, kind of just with my DoD background, you know, the intermediate modulus continuous fiber composite at 60% fiber volume has always kind of been the standard that I work to. And so as people begin to push towards that, there's been a lot more interest in additive manufacturing with these systems. The big question keeps coming up is why? And that's because of the competition and the incumbents that are out there. You know, people in the composites industry consistently think, hey, we've always been additive, and they're correct. And there's been automated systems that are able to, you know, if you look at toe placement, filament winding, tape placement, you know, and the automated systems doing that, they are additive. So why would we look at being able to look at these systems? And first is what AM has always been good at. It's the rapid prototyping and the tooling approaches. The reinforcement was originally kind of added in CTE and shrinkage. I actually did a polymer tooling for a 12-foot diameter containment case back in the mid-90s. And we first made our AM tools with just polymer. And because we were having some moisture problems and CTE problems, we actually threw a little fiber particulate into there to help with that CTE and shrinkage. So that's kind of the first kind of start at it before people started going after material properties. The low volume manufacturer, again, the cycle time is classic AM. The flexibility when you look at these materials and processes on the other side there, complexity, and then capabilities, right? I'm able to build something that can't currently be built. A lot of people are talking about how that's a strong point. It kind of becomes a weak point when you start talking about qualification certification. So that's a two-edged sword there. The materials and processes, here's just kind of a list that I put together quickly. It's extensive. There's lots of options. We can do it in thermoplastic and thermoset. I think the biggest thing you see nowadays is the change in the type of format where we're going, you have short fiber, long fiber. People are beginning to say they can print with continuous, and then, have everything from pre-preg sheets to slurries to tough, which is a new format that I did when I was at DARPA, where you actually have oriented high fiber volume short fibers. The reason why there's a lot of pushback and interest in the subjects because who the incumbents are. Injection molding sitting there, and at some point, the volume of parts that you're putting through injection molding, you can afford the mold, and it becomes kind of the approach you do. Everybody in the composites industry, whether it's AM or standard, always ignores high-speed machining. Should be not manufactured, but high-speed machining, and the use of tooling board as a format for making tools. I mentioned before automated fiber placement and automated tape laydown. Pick and place resin infusion molding has been around for years, and so the systems begin to look very similar when you look at what these systems are doing, and the AM systems that are coming on board. They're very similar. The way that I always kind of, especially when I was at DARPA, and I looked at this because a lot of the systems that are coming out today, people were approaching me when I was at DARPA for money to go do those. And I basically looked at metrics versus incumbents. And for me, the big thing is performance, fiber volume, orientation control, material properties, the throughput, maximum pounds per hour, plus realized pounds per hour. Even on the fiber placement and tape layup machines, they can put down a lot of pounds per hour with the right configuration and material. But if you have something with a lot of cut and add, and you constantly have to sub out rolls into your machine, there's a realized pounds per hour, and I like to know both those numbers. And of course, that ends up leading into costs. The capabilities and constraints of these things. Right now, people are, whether it's a size constraint, thickness, the radii, the complexity you can do, those matter. And, if somebody is sitting there and they're talking about taking a continuous carbon fiber and turning it on the dime and giving me a 1/16 of an inch radius, I'm going to have questions about that because more than likely you're failing the fiber. And so those constraints and understanding them, I think, are really important. And then the qual and cert, it's repeatability and maturity. One of the things I talked about before, when you do these things that are really complex, that's great. But at the end of the day, you got to qualify and certify that part. In the composites industry, and I go back into the early 80s with that industry, we always talked about how we could put the fibers in the direction of the load. And we can still do that. Of course, you can do it with the fiber placement machines. But the issue is everything that we fly is a quasi layup. And the reason for that is simplicity in the qualification certification process, as well as the design process. And so that, those things, when we start talking about what's new and what's old and what works, I think these things are all in consideration. So with that, I'll turn it back over to you, Kevin. Hopefully I hit some of the questions you were looking for.
Craig from AFRL to talk about, what are people looking for in terms of processes and materials and properties.
So thank you, Kevin. Can you hear me?
Yes, thanks.
Awesome. Thanks, Kevin, for the invite, and welcome everyone. So I'll just cover briefly some of the activities that we've engaged in for the past 5 years, where we started, why we decided to go down the path we did, some of the initial requirements we established for ourselves, and where we see ourselves going into the future. So we started in, at least me personally and some of my colleagues started in the polymer additive manufacturing area about 5 years ago. And early on, we took a look around and we saw that we didn't think at the time that additive manufacturing, at least for structures, wasn't quite where we thought we wanted it to be. So in order to get our feet wet, we decided to focus more on using polymer additive manufacturing for tooling applications. We really saw that as low-hanging fruit that we could mature in the near term, while some of the continuous fiber and maybe chopped fiber technologies came up to speed. So that's what we focused our initial activities on. We looked at a variety of different additive processes, which used different thermoplastic materials. And ultimately, and I don't want this to be a sales pitch for a particular process, that's not the intent, but we ultimately selected the BAM process for large-scale additive manufacturing tooling. But then as we kind of went down that road, we discovered, given some of the requirements that we had for our tooling, which included the ability to cure at 350F at 90 PSI. So we wanted an autoclave capable tool. The tool had to have a tolerance of plus or minus 15 thousandths of an inch. And we had a surface roughness requirement of 125 RA. And then, of course, vacuum integrity, that's always important. So our vacuum integrity requirement was about 28 inches mercury vacuum with a 1-inch loss over 5 minutes. So just to kind of highlight some of the requirements that we established up front. And as we looked at the big area additive manufacturing process, we discovered, or we realized up front, that there were going to be some significant challenges using that, just because of the way that those tools are built. It's built in the Z or in the vertical direction, which for larger tools would require us to split the tool up into multiple pieces and then join those together. And those joint areas was really where our biggest concern was, both in terms of structural as well as vacuum integrity, both in the short and long term. So fast forward, we caught wind of another FDM process that's being developed and is offered by Thermwood. We pursued that, and actually at the end of this project that we've had with Boeing, it's been very successful, I think. The tool that we fabricated is only 5 feet in length. It wasn't the original 10 feet that we had anticipated. So what we did is we actually had them build 2 5-foot tools so we could process one at 250F and another at 350F. But it met all the requirements in terms of tolerance. It was at about 5 or 6 thousandths of an inch maximum deviation, so it met our tolerance requirement. The surface roughness is anywhere between 65 to 120 RA, so it met that requirement. We've tested the vacuum integrity of this tool, both at room temperature and at 350F. It met that requirement. So we're really pleased with the performance of the tool. And I guess I would say, as of today, in terms of tooling using polymer fiber filled, these are carbon fiber filled materials. In this case, it was PESU. I think for I think for prototyping activities, that technology exists today. That can be used today for prototyping. Now, the real question comes in, well, yeah, it's great for prototyping, but if I need to build multiple parts, how many parts can I get out of this tool? And that's still the holy grail question that everyone's asking and that we're working on at AFRL. We also did a cost analysis on these types of materials, on these types of tools, and showed, for very mild contour, moderate contour, and complex contour shaped molds, that it really didn't matter. That was a very little impact on the overall cost of these tools, and that's one of the strengths, I think, of additive manufacturing. It doesn't, in terms of part complexity, typically, at least for large-scale tooling, that does not impact cost very much. So some of the cost savings that we saw as we compared additive polymer additive manufacturing to traditional composite tooling like aluminum, Invar, high temperature composite, foam tooling, we saw anywhere from one and a half times less the cost up to 3.5 times reduction in cost compared to some of those other processes. So very promising. In terms of where we want to go in the future, and you're going to hear from Nathan Stromberg at Continuous Composites in just a minute, but we're very interested now as some of these additive manufacturing processes that are more dedicated for the fabrication of structural components. We're very interested to begin establishing requirements for some of those. We haven't established those yet, but as we get started with organizations like Continuous Composites and others, we anticipate establishing those same requirements as we've done for tooling. And so with that, I'll turn it back over to you, Kevin.
Move on to Jeff to talk about 3 of our material process combinations today. Jeff is from Impossible Objects.
Thank you, Kevin, and thank you all for joining today. Okay, next slide, please. So with the Impossible Objects technology, we're going to start off with the different material combinations that you can run in this composite lamination process. I also like to think of it as kind of a toolless compression molding technique. And this is really where the material combinations come into play with the Impossible Objects technology. We're using basically pre-preg sheets, pan carbon fiber sheets or fiberglass sheets. These are non-woven sheets that have fiber lengths of anywhere between 12 to 25 millimeter length with a random dispersion in the sheets. They come with different binder types, but that's basically the pre-preg sheets that we actually will be building with in this process. Now, the matrix materials, we have thermoplastic matrix materials that are commercialized right now, and soon in the very near future, we will have in a thermal set epoxy matrix. Some of those matrix materials that are available today are PEEK. As many of you are on this call know, that's a high temperature and chemical resistant thermoplastic material, as well as various nylons we have available to run in this particular lamination process. The thermal set epoxies basically is really interesting. Besides giving you the end properties of a thermal set composite, the processing time of actually making a thermal set composite is much faster than doing a thermoplastic composite PEEK part. It's about half the processing time. But the overall benefits is that you got a number of material combinations that you can work with, far as with the fiber sheets, the matrix materials that give you a strong, lightweight, chemical resistant materials to choose from. Next slide. The way the Impossible Object process work, known as CBAM, composite-based additive manufacturing, is it's a 3-step process. Starting with step 1, basically we take those pre-preg sheets, feed those sheets onto a print platen, and using an inkjet print head with 600 dpi resolution, we actually take your slice file from your CAD file, and we actually wet out the image onto the pre-preg sheet. After that occurs, the sheet automatically flows underneath a waterfall of either a thermoplastic powder or an epoxy thermal set powder, and that will stick to where the wetting fluid was placed onto the fiber sheet. The next step is that all excess powder is blown and vacuumed off. This is all done at room temperature, so there's no thermal effects on any of the thermoplastic matrix materials. The sheets are automatically stacked, and then that completes the printing process. The second step is that those sheets are then transferred into a heated press and taken up to the melt point of either the thermoplastic or thermoset material. Once you reach that melt point, for peaks, it's about 380 degrees C. For nylons, it's about 200 degrees C, and for the thermal sets, it's about 185 degrees C. Once you reach those set points, and then basically we press them together, and that's where you're forming your thermoplastic or thermoset composite parts. At the end of the pressing process, we go to the final step into a removal cabinet and remove the unfused fibers from the build block to get you to your finished part. Fiber volume content for this particular process is about 25%, and so that's how the process works. We can go on to the next slide, please. So one of the interesting things is that when you compare this to powder bed systems with smaller fibers under 1 millimeter in length, or extrusion-based systems that it's usually under a 0.5 millimeter in length, they are going to give you a little bit of a performance gain far as strength, electrical, and thermal properties on that front. But the real advantage with this particular process, we're basically forming the parts under pressure and temperature in that heated press, and therefore the warpage and curl issues that you typically see with some of the other additive process doesn't yield itself. And having said that, you get really nice surface finish. You get some pretty good part tolerances. 0.005 of an inch or 0.012 millimeters is overall tolerances that we measured to date, but it's the warpage and shrinkage issues that are controlled and well maintained in this process. Last slide, please. And to kind of tell you where we're at with the different material offerings that we have today as far as mechanical properties, this is, you can see in the chart here, we range anywhere from kind of on the low end of 115 megapascals up to 144 megapascals as far as tensile strength, depending on the matrix material and the non-woven selected. And you can see the tensile modulus kind of go from anywhere from 8.5 gigapascals up to about 12.7 gigapascals. But that's kind of where we're at. That's basically kind of a quick flyby of the Impossible Objects composite-based additive manufacturing technology.
Next, we will next we'll switch to Scott Turner to talk about 3D systems, processes and materials.
Great. Hi, hope everyone can hear me. My name is Scott Turner. I'm with 3D Systems. I currently work on advanced systems and technology for the company, part of advanced research. My background in additive and I guess composite materials started in 1988. I was one of the company's first training instructors and got involved in the stereolithography process at the very inception. So composite materials are very interesting to myself and 3D Systems and companies. They started with simple things such as conventional fillers, you know, maybe talc powders in the very early days, to much more advanced materials today, in which we try to create polymetric networks that are both functionalized and non-functionalized. Yeah. So anyway, I think I'm thankful that Kevin invited me to the group, to share some of the experiences we have, some of the products. There's been a lot of really good material science developed using fillers, both short fibers. So we have commercial thermoplastic nylon that's reinforced with short fibers. that provides really good mechanical properties and has been a market-leading technology for small UAVs. But you know, the potential of composites, I think to some degree, is still untapped in how we continue to evolve and develop these processes and carrier materials to really get to some of the conventional and incumbent processes that we support today. Back in the early 90s, you know, I too tried to use additive in the more conventional composites, starting with resin transfer molding. And how do you apply different types of materials and geometries to those processes in support of composite materials derived from often additive tooling or fixtures. The area that 3D Systems is most interested in developing today, and I'll share to the degree I can, is in our Figure 4 photopolymer systems, which allow really high speed polymerization of these polymers. And then what we're doing to integrate in all kinds of filling materials, starting at both the nanoscale and moving up into short fiber, and then, you know, with an eye towards how do we move that into a continuous fiber. So, you know, the nice thing about having almost 35 years of experience in these approaches, we know a lot of things that don't work, and you know, they don't derive enough benefit to the part and the application of that part to meet the value proposition associated with doing it over these incumbent methods. So again, I'm really happy to be here with, you know, representing 3D System and some of the technologies we have in this space, and learning and sharing from some of the people on the panel that are you know, more of the tip of the spear these days, developing some emerging approaches to these problems. So thank you, Kevin, and I'll turn it back over.
Providing that perspective on that and the different complexities that are involved. Finally, we'll move to Nathan Stromberg from Continuous Composites.
My name is Nathan Stromberg. I'm the engineering manager at Continuous Composites. My background is in mechanical engineering and automated composite manufacturing. So I was developing automated fiber placement, automated tape laying, and filament winding processes before joining the team here at Continuous Composites, which has a lot of synergies with what we're doing here. You can go to the next slide. So Continuous Composites is developing a new composite manufacturing technology called Continuous Fiber 3D Printing, or CF3D for short, which takes the advantages of additive manufacturing and composite materials and combines them together while eliminating many of the constraints. Go to the next slide. So when we look at traditional composite materials, they're used because of their superior strength to weight ratio, their low CTE, and their non-corrosiveness, but they're limited to high-end applications because they're very labor-intensive to manufacture, require costly tooling and molds, large autoclaves. There's a lot of material waste in the process, and all of that results in high cost, long lead times, and slow design iterations. Next slide. Additive manufacturing, on the other hand, is really great for going from the digital to the physical world very quickly. You can rapidly design different iterations, print one part one day, different part the next day. There's minimal waste because you can print in that shape. You can print on demand, and it can make very complex geometries. But AM is traditionally constrained by the material systems that are available, which are weak materials. It's a slow process and typically constrained to small build volumes. Next slide. This is where continuous fiber 3D printing comes in. Next slide. So CF3D is a shift in the way you manufacture composite materials. It leverages the benefits of composite materials, additive manufacturing, and robotics to eliminate the constraints of the traditional processes. It introduces a true continuous fiber to additive manufacturing, utilizing snap curing thermoset resins to dynamically steer fibers and eliminate tooling. We offer a diverse library of fiber and resin systems and material combinations, and it works for many different applications, including structural and high temperature composites. Next slide. On the right here is a simplified process diagram of how the CF3D print head works. It starts in the top right with a dry fiber spool. It can be carbon fiber, glass fiber, or any of the others listed. Besides that, it's a dry fiber, not a pre-preg, because we're eliminating that pre-pregging process. And that dry fiber is impregnated in situ in the print head during the process. The wet fiber is then discharged, consolidated against the part surface, and snap cured in place, creating a moldless and out of autoclave manufacturing process. Next slide. So in summary, CF3D has superior strength to weight ratio because it's using continuous composites. It's a low-cost material process or low-cost manufacturing process because it's automated, uses inexpensive dry fibers. You can print net shape, so it has very high material yield. It eliminates molds and tooling as well as autoclaves. There's freedom of design. You can make complex geometries. It's not limited to just 2D stacking. You can go through rapid design iterations because you're not having to create new molds every time that you want to test a new geometry. And we'll talk more about printing functional materials later. Next slide. The first hardware solution that Continuous Composites is bringing to market is called the CF3D Enterprise System, which is a customizable work cell where you can increase the number of axes or the build volume depending on customer needs. It's got integrated safety system with UV filtering and ventilation built in, and it utilizes a customized robotic arm where Continuous Composites developed an infinite joint 6 for the robotic arm, and we integrate it with a Siemens 840D CNC controller for high accuracy. It also has automated tool changing, so you can change out the print head automatically for different print heads loaded with different materials for changing materials within a single part, or it can be swapped out for other finishing tools. In addition, the print surface can be quick changed out and replaced with different configurations, such as a rotator or rotary table. Next slide. Continuous Composites is also developing software to drive CF3D. Our software bridges the gap between traditional manufacturing and the unique process of CF3D. It's an anisotropic toolpath generation software that optimizes the process parameters to improve composite quality, tolerance, and speed. It has print simulation and visualization built in to detect and resolve issues before they happen. And it integrates with our materials database of pre-optimized fiber and resin combinations. It also has continuous fiber infill and junction optimization built in, and it's an end-to-end solution for toolpath generation with CF3D. Next slide. On the materials side, I mentioned that we use dry off-the-shelf continuous fibers, so it can be any aerospace grade carbon fiber or fiberglass. Also print with aramids. And then we combine it with the liquid snap curing photopolymer, which we're developing a library of for different applications. So applications range from flexible materials to rigid materials, high temperature applications, and we also have specialty resin systems, such as one for creating carbon-carbon composites that pyrolyzes and converts into carbon. We can also print with functional materials such as nichrome wire, copper wire, fiber optics to build functionality directly into the composite part. Next slide. This is a snapshot of some of our achievements in materials to date. So we're hitting high fiber volume fractions above 60% while maintaining porosity below the standard 2%. And one of our resin systems that we've recently developed is a high temperature resin that has a glass transition temperature of 227 degrees Celsius. Next slide. And behind CF3D, Continuous Composites has 75 granted US patents, 31 international patents, and many more in the various stages of getting granted. So we have the technology locked down from an IP perspective, and we're excited to bring it to market. Next slide. And that's all I have today. I'll pass it back to Kevin.
I'm not going to follow for a couple of minutes with a few questions as people are going through, and then we'll open it up to the audience. So if you're out there in the audience and you have a question you want to ask either to one or more of the participants, go to the Q&A and put them in. And then additionally, you can, one of the nice things about the Remo platform is you can, if someone's already pretty much asking the same question, you can just click on it. And as the question gets extra votes, it moves up in the list. So my first question, I'm going to direct towards to Mick and to Craig. Traditional, laminate composites get very, used in aerospace, get very intensive non-destructive testing, 100% volumetric inspection, ultrasonic, perpendicular to the layup direction. Whereas at the other end, right, your polymer matrix or your polymer AM parts generally have been, pretty light in terms of inspection, a visual, maybe an optical, shining the light through. Where do you kind of see the transition as we go into both of them? Where a more, fiber matrix composite type NDT regime would be required.
So I'll take a first crack at it. So on my open manufacturing DARPA, we work closely with the airworthiness folks at both the Navy as well as ATEC, which was the Army Test and Evaluation Command. So these are the guys that actually sign off on the use of these materials and designs for the platforms. I think as you go to a structural part, the NDT requirements are going to step up because it's, there's plenty of parts that don't get NDT inspected that are of high quality. It's not a knock on them. Where this requirement comes is basically building confidence in the part that when you put it on the aircraft, it's going to perform as needed. And so it's really driven by the qualification certification requirements of the design and component and material and manufacturing process as you move up into more critical parts on the aircraft, or even for DoD, armor vehicles, right? So that's what I think is going to drive it.
Thanks, Mick. Craig?
Yeah, so I agree with what Mick said. Just want to add a little bit to it. It certainly is going to be a challenge, I think, for qualification and certification of some of these flight critical parts. And what I see happening more recently on the ATL, automated tape layup, and fiber placement technologies is where they're introducing more in-process monitoring technologies. And I think, especially for some of these technologies that were introduced today, that might be a key feature that will be necessary in the future for some of these qualifications. We're always going to need, a post-manufacturer inspection process, but I think to go along with that, at least in the near future, we're also going to want to make use of some of these technologies that are coming online where it's in-process monitoring.
Thank you. I have my second question. I'm going to direct towards Jeff in terms of your process. What types of fiber orientations are you able to achieve with Impossible Objects technology?
So right now, the non-woven sheets have a random dispersion. That's where we're at today. Mm-hmm. There is potential for the future, and I want to highlight future. And we've done an initial first look at this of taking some of the unidirectional stretch broken materials so that you can actually use unidirectional materials in this process, but it's something that we're not too far down the road with. But current state is random dispersion, non-woven sheets, Kevin.
Still, but it's still a sheet process. So you're pretty much in the XY plane versus orienting everything.
Yeah. And we could in the future, again, this is future state, of putting a turntable in there to get your quasi-isotropic layups on there, your plus minus 45s and 90s in there, of putting a turntable into the technology to do that. But that would only be useful if we had a unidirectional sheet.
Okay. All right. Thank you.
Thank you.
My next question is, you probably guess this, is for 3D systems. You mentioned short fiber. What actual process, is there a core polymer AM process that you're using? Is it laser powder bed fusion based? Is it extrusion based? Are there both, or is it something different?
Sure. So it's all of the above, actually. So what I see in the technology today is, we strive for these structural aerospace parts with rigorous requirements and inspection. But in between that and a non-reinforced polymer part is a lot of opportunity to stretch the material properties for specific customer application. And that's typically what we've done is, we'll have a process and a material, but not quite good enough from either, let's say, a modulus standpoint or a toughness in an application for production. And so we can use composites to enhance or adjust those properties for a very specific need. One of the earliest ones was simple wind tunnel models. By using nanoparticles and highly filling photopolymers, we were able to produce really stiff structures that could simulate even metal components in the final wind tunnel part and give really valuable data at those times. So, I know there's a lens of just the highest performance application, but in the middle, there's a lot of things that can benefit from composites of either thermoplastics or photopolymers.
Thanks, Scott. Actually, it turns out the question I had for Nathan was one of them that showed up in the Q&A session. So instead of me asking it, I'll just wait for that to come up. So we'll transition over to the audience Q&A section, and I'll start with you, Nathan. So the first question we had is, are the materials used for continuous composites recyclable?
Yeah, it's a great question. So we've chosen to focus on thermoset UV curable materials. And the reason that we're focusing on those is because thermosets are superior in mechanical strength. With additive manufacturing, you get a cross-linking between layers for good shear strength and also transverse tension. And then we focus on photopolymers because they snap cure as they come out of the printer, which allows you to fiber steer and make complex geometries that you wouldn't otherwise, and also print at very high speeds. So because we're using thermosets, they're not recyclable. We could focus on thermoplastics in the future, but just our go-to-market strategy has been to focus on thermosets.
Okay, thank you. The second question, I'd say, this is for the full audience. It was asked by Karen. What kind of, do any of the three processes, do you have a sort of a initial and sort of a sweet spot and sort of an ultimate type of applications you're looking at for them? And either the three of you feel free to answer in whatever order.
Yeah, this is Jeff with Impossible Objects. Kind of the first area is tooling. To Craig's point, with any new emerging technology process, you can learn a lot and mitigate your risk by starting with tooling. And some of the tooling areas that we've worked with has been in the electronics area for like wave soldering pallets. They're typically carbon fiber PEEK. So they see temperatures, they go through chemical washes, and so that is kind of a first area for the use of the impossible objects technology. Second to that, when you start talking more commercial applications outside of tooling, we're looking at drones, particularly for secondary or tertiary structure, not so much for load-bearing structure that Craig was getting to, but looking at, you know, what kind of complex shapes and parts can we do, like propellers, for example, on commercial drones, or even some of the air mobility markets. We're into that as well, looking at tertiary and secondary structure.
Thanks, Jeff. Scott or Nathan?
Yeah, you know, I think the UAV market has been a strong adopter of these technologies, and specifically for us with our selective laser sintering and fiber reinforcement of that material, it was a simple problem in ballistic launch. So a very specific challenge for a very specific customer for a very specific application. And by custom blending a thermoplastic composite, we were able to meet that requirement and produce the part of the program. So I think what you'll see moving forward is just a kind of a broader adoption through the collaborative method. So in some cases, people are going to be looking towards thermoplastics to carry composite materials for purposes that range from heat conduction to other needs, a specific load-bearing case, to photopolymers, and then into other materials. So that's kind of how we're looking at it. It's very specific use cases, even down to a part level.
Okay. And is that, yeah. And Nathan?
Yeah, so because continuous composite, or because CF3D is a low-cost manufacturing process, our industries range anywhere from consumer goods all the way up to Department of Defense and space. And so when it comes to certification, there's many industries that we can currently use CF3D in that have very low levels of certification, very easy to get into. But we're also working with the Air Force and these various industries, but the Air Force in particular for LCAT vehicles, UAVs, and kind of getting rapid certification started.
Thanks. Actually, a follow-up. The next question is also for you, Nathan. What is meant by the junction adjustments with CF3D?
Yeah, good question. So we have algorithms in our software for how to handle the junctions. So depending on the direction or the load that the junction is under, whether it's tension or torsion or other, we can steer the fibers. Just think of like a four-way junction. You can steer the fibers through the junction, or you can take a corner with the fiber. So kind of each intersection you come up to, you have three different paths that you can go. And so, and you don't have to go the same direction with each layer. And so basically they're algorithms which tell the tool pathing which direction to go through the junction, depending on what layer you're on.
All right, thank you. Can you follow up a little bit, Nathan, as well on snap curing? That was another question that was asked.
Yeah, no problem. So we use, like I said, thermoset photopolymers. So they're UV curable and they snap cure within milliseconds. So that's what allows us to print very fast and also take corners.
And now, let's see. You had mentioned 63% or so you were achieving, and your
Yep.
volume fractions. I'd be curious to also ask, impossible objects and 3D systems. What sort of limitations are you seeing in terms of volume fraction for either fibers or for particulates? Yeah. You're still muted, Jeff.
Oh.
There.
So with the CBAM process, with the current use of the non-woven sheets, we're getting about 25% fiber volume fraction. Now we can go to longer fiber sheets, unidirectional sheets, but what the determining factor will be there is the diameter of those fibers as well as the weight, the final weight of the sheet. With the thermal set epoxies, as well as some of the other thermal set materials that we're evaluating, we're getting better viscosity and flow through the fiber sheets. So we think that we're going to be able to, once we make that move to unidirectionals, is see much higher fiber volume fractions, certainly close to 50%, if not greater than 50%. But to achieve 60%, I think that's going to be probably something we can achieve. But 50% is certainly in the cards.
Thanks, Jeff. Scott?
Yeah, so in terms of the applications that we've been working in and addressing, it's mostly material property enhancement. So we're very low ratios, so typically below 50%, well below 50%, both in thermoplastics as well as in the photopolymer materials. We have a great appreciation for the challenges that I think additive in general faces in trying to meet some of the incumbent methods, densities of fiber, and really kind of achieve similar ratios with similar properties. So I think that's an area of exploration for all of us in the near future.
Is there a reason why CBAM, your fiber length, is limited to 25 millimeters? Is that a limit, or is that just a choice you've made so far?
Kevin, that's impossible objects, CBAM.
Oh, CBAM. Sorry, Jeff.
So no, that's just a current choice with the starting point with the non-woven sheets. So we can certainly go longer than 25 millimeters.
All right. Well, that will end the sort of the I'll say called the forum session of our webinar. For the next 25 minutes or so, we'll break out into our individual tables and allow people to ask detailed questions with our panelists.
And I will mention as well that we did record this session today, and we will be sending it out to everyone who registered. So you will get a follow-up if you have the content or ask any individual questions to our panelists at a later time as well.
Okay.
So thank you. Thank you. Well, we're going back to the floor now. So if you'd like to talk to somebody, just double click on the table where they are seating and you can join their table. Thanks.